Hi, this is Dave Johnson. Welcome to another edition of Math Off Topics. Today I want to talk about integration and, in particular, why do we need integrals? You probably have already studied integrals in your calculus class. You may hopefully have done your antiderivatives. You know how to find an indefinite integral. You have seen the definition of the definite integral in terms of a Riemann sum, may have even taken the limit as n goes to infinity of a Riemann sum. And probably you've learned how to evaluate a definite integral using the fundamental theorem of calculus. And no doubt your teacher has told you that the definite integral is the area under a curve. Um, What's the big fuss? Why does anybody care about the area under a curve? I mean, is the world defined by areas under curves? Well, yes and no. So, what I want to show you is how we can think of integrals as areas under curves, but that can have some real practical application. So, let's get into it. So, let's imagine for a moment that you own an oil well. And I ask my students this question every time I talk about this. I say, well, how many of you have an oil well? Probably not very many. I live in Texas, so a few of us do. I don't own an oil well, but some of my students, their grandparents might own an oil well. And one of the things you figure out if you do have an oil well on your land is the rate of production of the oil will go down with time. Why is that? Well, the pressure under the ground, maybe it gets less and less as you pump more oil out of the ground. And so if we think of the rate of oil production as a function of time, you can see from this graph that that rate is decreasing. Okay. And let's suppose we want to figure out how much oil is going to be produced by this well. We can measure the rate of production. We know how much oil is coming out of the ground at any given moment, and we can keep track of that. And somebody does, right? And so let's say that this rate, we're going to call this f of t. And so this function is f of t. And so now we'll talk more in detail about what f of t really represents in a moment. But suppose I want to find the area under the curve. Why would I do that? Well, we'll talk about that in a moment. So suppose we take a little sliver, and I'm going to draw this sliver here. And let's say this is a delta t amount of sliver. And maybe that represents one day in the life of this oil well. Okay. And so if f of t is the rate of oil production, what might that be? Well, barrels of oil per day, let's say. And so if we take the f of t and multiply that, so f of t times delta t, well, if this delta t represents one day, then we have f of t times delta t is barrels per day, which is our f of t, times the number of days. Let's assume that delta t is a measure of some number of days. And you see that the days cancel, and what you are left with is that f of t times delta t is equal to barrels of oil. So f of t times delta t is a number of barrels of oil produced in that little delta t time slot. So now we want to find out the entire production of oil. So we could, if you wanted to, we could slide this delta t back and forth along here. I'm not showing all of the different rectangles, but here we have, we can add them all up, okay? And that's what an integral does, right? So the integral, and let me draw it this way. So the integral from 0 to t is the ending day when we are done measuring our oil production. Maybe it's we decommissioned the oil well at that time. F of t dt. Well, what is that? That's the limit as n goes to infinity of the summation I equals 1 to n of f of t sub I, let's say, times delta t. And so this f of t sub I times delta t is exactly what we found in one of our little slivers, f of t delta t. And so finding the total oil production is the same as finding the area under the curve. Okay, so the this integral is the total oil production from the initial day times 0 to our final day t. And so how does what's the importance of the area under the curve? Well, in this case, the area under the curve represents the total amount of oil produced. Now, you might say, well, that works for oil production, perhaps, but what's the big fuss? Why do we study integrals? If you didn't have an integral, if you couldn't do the integral, you wouldn't really know the exact amount of the area under the curve, the exact oil production. Um, but there's a bigger thing going on here, which is this is always going to be true. This sort of thing is always going to happen. So let's talk about this in more detail. If our f of t was a rate of production, I can call that, let's say, dq dt, because, well, it's the amount of oil per unit time, and q is the total amount of oil. And so we could say this is big Q here, Q total perhaps. And so dq dt is the rate at which oil is produced, and we're calling that rate a function of t. And what if we multiply both sides by dt? And we can do that because dq and dt are both differentials. We learned earlier in your calculus course that dq and dt are differentials, and they have algebraic behavior. We can treat them as algebraic quantities. And so if I multiply both sides by dt, I get dq is equal to f of t dt. So when you see a function as an integrand, that can always be interpreted as a rate. Always. If you're doing an integral, that's really what it is. It could be the rate of dollars per day. It could be charge per volume, so some sort of rate. And now if we integrate both sides, so I'm going to integrate the dq, that's the same as integrating the f of t dt. But what is f of t, the integral of f of t dt? If we integrate from 0 to t in both of these cases, what have we done? We've produced an answer which is our quantity q of t. And so q of t, the total quantity of oil produced, or whatever it is that we're measuring here, is actually the integral from 0 to t dq. And so think about the integral dq is q. And we can generalize this idea. The integral of mass, little dm, is total mass. The integral of charge, we could also call that dq, is the total charge, and so on. And so there's every integral that you're going to see. Now I say that somebody out there could dream up an integral which isn't of this type, but in practical terms, in engineering or physics or biology or business or a lot of these fields, the integral is the integral of some small quantity. You're adding up all these little tiny quantities, dq's. You're getting a total oil production, charge, mass, whatever it is, and that is equivalent to the area under the curve. And so next time your teacher talks about the area under a curve, don't think geometrically, think in terms of quantities based on these rates. So I hope this has been helpful. If you found the video helpful, subscribe to my page, give it a like, and I'll see you next time.